So we all know that large language models make silly mistakes, from big multiplications to hallucinating information. Now, what the authors of this paper, Faith and Faith, Limits of Transformers and Compositionality, ask is whether or not transformer-based models are actually uncovering rules for problem solving and exploring true reasoning paths when they're solving problems, or are they just doing some fancy pattern matching between input and output features? The authors argue that these silly trivial mistakes might indicate a lack of ability to perform compositional reasoning in transformer-based models, arguing that actually what transformers are doing are just reducing multi-step compositional reasoning into some linearized graph matching. To evaluate the compositional reasoning abilities of transformers, they settle on 3 tasks to assess these capabilities: a long-form multiplication task, the Einstein puzzle, and a dynamic programming problem. Now, these tasks were chosen based on the fact that they're centered around compositionality and that they require the combination of reasoning operations with following a computational path to arrive at a correct solution. They form 2 hypotheses for this paper. The first one is that transformers are actually reducing multi-step compositional reasoning to linearized graph matching, which is something that is thought to contrast with multi-step reasoning that learns to apply computational rules to reach correct answers. The second hypothesis is error propagation, which is this idea that because transformers may have inherent limitations in solving high-complexity compositional tasks that exhibit novel patterns, errors in the early stages may lead to substantial compounding errors in the subsequent steps, preventing the models from reaching correct solutions. To investigate these hypotheses, they formulated compositional tasks as computation graphs, breaking down problem solving to submodular functional steps, enabling structured measurements of complexity and the verbalization of computational steps as input sequences to language models. Now, here in figure 1, they show an example of a computation graph for a long-form multiplication algorithm A with inputs 7 and 49. They used graph metrics to quantify complexity. They used reasoning depth as a proxy for the maximum level of multi-hop reasoning required to solve the task, reasoning width as the maximum number of variables required to keep in parallel during the computation, and average parallelism, which is the average width in computation through the graph. They use this approach of predicting surface patterns to relative information gain to assess the strategies for partially correct answers models use in incorrect responses. You had 3 tasks for this paper. The first one was multi-digit multiplication, where you have to manipulate symbols through the usage of procedural rules. You had the Einstein puzzle, which involves a list of houses and a list of attributes, and you have to associate the attributes with the houses through the usage of clues and constraints. And you had a dynamic programming problem that reads as, given a sequence of integers, find a subsequence with the highest sum such that no 2 numbers in the subsequence are adjacent in the original sequence. Now, here in figure 2, they show that the zero-shot accuracy of the models decreased as the problem size increased in each of the tasks. And they also showed that the average parallelism, which is one of the metrics they use to quantify complexity, was negatively correlated with the accuracy of the models. Now, here in figure 3, they show that the GP3 fine-tuned exhaustively on task-specific data only did well in examples present in the distribution. Now, one of the things the authors wanted to understand is why is it that transformers can predict partially correct answers when the overall response is incorrect? Now, they hypothesized that that was the case because of peculiarities in the task distribution that allowed the model to guess partial answers without performing the multi-step reasoning required to solve the task. Here in figure 4, they show examples of poor generalization for the GPT-3 in the puzzle and DP tasks. Here in figure 5 and 6, the authors are showing how the ratio of correct nodes, meaning correct partial solutions provided by the models, decreases as the problem size increases in terms of the number of graph layers, which is one metric they use to quantify complexity. Finally, the authors present a mathematical argument showcasing why it's the case that as the problem size increases, the chance of the models to produce a correct answer decreases exponentially. The authors conclude that transformers often solve multi-step compositional problems by collapsing the depth of compositional operations via analogical pattern matching. Now, there are a lot of things that I liked about this paper: framing problem solving as computation graphs, quantifying complexity to these graph metrics, and showing strong evidence of the limitations of transformers for compositional reasoning. If you like this video, don't forget to like and subscribe, and see you next time. Cheers.